Let's look at the area of triangles, and I'm going to apply it to a problem straight away so we can see it in context. The problem says we need to solve x equals what? X is that yellow angle in here. We don't know what it is, we want to know what it is, and moreover, you've been given, it's not stated clearly here, but you have been given an area, let's get this, an area of 4 centimeters squared. So that's what the area is. In fact, what I'll do is just so we can keep coming back to this because I don't judge it's made clear enough throughout this. This area in here is 4 centimeters squared. You have two lengths, 4.1 centimeters and 4.1 centimeters. And so we're going to solve this problem, and in so doing, what we're going to do is we're going to end up having a conversation about the area in the detail necessary for us to be quite comfortable with the area of triangles for any geometry problems. So let's begin by considering this triangle in front of us. This triangle here is born from the idea that we have this angle in here, so assume that that is theta. And theta, opposite theta, of course, if I was to take my little arrow and I said to you that the opposite theta is there, which is the height of this triangle, this right angle. So this is opposite. And it seems to be a bit intrusive on the opposite there. So let's say like that. Hypotenuse is always the longest side, and the base is often called the adjacent side, not capital A, we use little a for that. And what we're going to do is I want to consider this. This is not what we have here, of course. This is an isosceles triangle, but I want to begin here. And what I'm going to do is I'm going to say, consider then that sine theta is opposite divided by hypotenuse. So sine theta is describes this construction here, this concept describes the relationship between opposite, hypotenuse, and theta. Opposite, hypotenuse, and theta. So that is to say, whatever size of hypotenuse there is on a right angle triangle, relative to the size of an opposite, there will be a specific angle so that it obeys the laws of what a right angle triangle is, which is one in which one of the angles is 90 degrees. Or an oversimplified way of suggesting it. I can take this concept of sine theta equals opposite divided by hypotenuse, the relationship between these three terms, and I can multiply both sides by h. If I multiply this side by h and I multiply this side by h, these two will cancel, leaving me with h sine theta equals O. And O, of course, is the opposite there. I'm going to utilize this later. So that is, I do not want that arrow. That arrow is very intrusive when you've forgotten that it's coming. There it is. So I'm going to utilize this. This is our step one of discussing the area. Be aware that h sine theta is equal to O. H is this length here, this length here. And of course, let's apply this to this, but in time. For now, I'm just simply looking at right angle triangles. Now, well, let's take a look at this box just for a moment before we move on to the next video. Let's take a look at this box. I'm going to split this box in two, like that. I'm going to say that, imagine if you will, this triangle is going to appear in this bottom bit. So for example, that is the opposite side. Let's say that this is the angle. Let's see if we can give it a bit more curvature. There is the angle, theta, as we've been describing. And just to aid in relating it to the one above, there is the hypotenuse. Now, what we know about this area is going to be half. This is going to be half of the base times the height. And this color does not do well when it's running through the pink hypotenuse. So we'll come here. I'm going to say that the area is going to be half the base times the height, like so. And so, what do I mean by base and height? I mean synonymous to this diagram. Base is at the bottom, the adjacent, height is the opposite. So the area is half base times height. Now, this you could describe is a right angle triangle. So what happens if, for example, I was to take this point here and I was to drag it, say, to over here, like that? Let's take a look at what happens. Then the hypotenuse, or that length there, switches, it moves upwards, and the opposite side changes to there. The angle becomes larger, like so. And that is as a result of me moving, this is where the arrow becomes advantageous, again, me moving from this point to this point. I can do this again, I can move it once more, even further. I might even do two more. Let's do a green. I can move my hypotenuse. It's not per se an hypotenuse at this point. We have to be very careful because I've lost the concept of it being a right angle triangle. It's no longer a right angle triangle, but it is this equivalent length, this equivalent side I have moved now, so it's up here. And again, notice what happens. The angle gets larger. It is a much larger angle. Another thing that's worth considering is that this length is decreasing in size and this length is increasing in size equivalently. Of course, the final position, if I kept going utilizing my arrows, let's get one more in of these. I think I was using red. The final position is to get all the way to the edge in which we'd get a right angle triangle again. Finally, I don't want to use red again. Let's have a go at some yellow, some yellowage. There is what will happen for this side here, which was used to be our opposite. It's now shifted all the way up to here, and this, what used to be our hypotenuse, has now moved all the way to. I'm not going to use that again. Let's get a black. You cannot see black. Let's get a blue. So there is this situation, and notice that again the angle has got much larger. I'm using blue. I've used blue before. I'm going to allow for a pass on that. That angle, damn, that's harder to do because it's larger. I'm just going to do this. This is the 90-degree angle now, and so it's a new right angle triangle. So hopefully you can see the pattern as I go back. The triangles shift within this shape. So the idea that the area is the half base times the height comes into question when you consider other triangles other than a right angle triangle. So for example, this isosceles triangle. Another question that might come to mind is, but does the area stay the same as I shift within this structure? And that's something that I think is definitely worth considering. Another thing, one final thing to consider is how do we take into account the fact that that angle is changing? And by the way, you can answer that question by utilizing the formulas that we're going to go for as to whether the area changes as you move around in that square. But what we're going to do then is we're going to consider the fact that the height, that length of the height, it changed. And it changed according to a certain angle, theta. Theta got bigger. The height changed. And we're going to need to consider that concept. So what we're going to do is this. We're going to consider that for the basic circumstance, here it is again, when I have just not paid enough attention to the arrow coming along. The basic circumstance is the area of a right angle triangle is half base times height. However, we might want to consider that the angle changes when you have different triangles. For example, if I was to go straight into the middle here, not to scale of course, but assume that is the middle, and there is the question, similar to this being 4.1, 4.1, assume that this is 4.1, 4.1. When you have this, the question becomes, can you simply use this formula? And we'll tackle that of course in a moment. And is there a way to take into account the angle theta here if you have been given it?